Hey, folks. Okay. So, in our quest to find planets that are more like Earth, we're trying to find, where should we look to find life in the universe? Well, we don't know. We don't know all the ways that life can happen in the universe. We only know, for sure right now, about life on Earth. And life on Earth sure does benefit from having liquid water. So, does all life in the universe require liquid water? Maybe, maybe not. We don't know. But liquid water sure is useful on Earth, and seeing as chemistry and physics behaves the same everywhere in the universe, maybe all life, or at least maybe most life, needs liquid water. Maybe they find it just as useful as we do. Seeing as we haven't found life on another planet yet, let's go with what we know for sure. And what we know for sure is life on Earth likes liquid water, so let's start looking for planets that have liquid water. Well, what does it take, right? What does it take for water to be a liquid? It's got to be at the right combination of temperatures and pressures for the water to not boil, not freeze, and stay liquid. So, imagine you find this planet. This planet Morix has a temperature of 350 Kelvin, has an atmospheric pressure of 1 atmosphere. 350 Kelvin. Oops. There we go. 350 Kelvin at a temperature of 1 atmosphere. Morix would be right there. That's in the green zone. So that's liquid. It's on the hot side, right? 350 Kelvin is warm, but still liquid. So, if there's water on planet Morix, the water would be warm, but still liquid. Dragel has a temperature of 350 Kelvin, but an atmospheric pressure of 0.003 atmospheres. And so remember that the vertical axis here is what you call logarithmic, right? They're taking this huge span of numbers from 0.00001 atmospheres all the way to 10 million atmospheres, and they're squeezing them together so that they all fit on this page. And they do it. How do you fit all those numbers in? You fit them in by changing the scale of the graph every time you go up a power of 10. So you read it like this. You start off with, let's say 0.1 atmospheres, right? You start with 0.1 and it's 0.1, 0.2, 0.3, 0.4, 0.5, etc. until you get to 1 atmosphere. And then once you get to 1 atmosphere, then it's 1, 2, 3, 4, 5, until you get to 10. And then once you get to 10, it's 20, 30, 40, 50, up to 100, and then 100, 200, 300, 400, up to 1,000. You see where I'm going here, right? So every time you go up a power of 10, you change the scale to that power of 10. So, if you're trying to find where 0.003 atmospheres is, well, start with 0.001. And if this is this is 0.001, so 1, 2, 3, there's 0.003. So if you have water at 0.003 atmospheres and 350 Kelvin, that'll be right there. Same temperature as the water on the first planet, but there's not enough pressure. There's not enough pressure to keep the water down in a liquid state. So the water's just going to boil away. So, will the water be liquid? No, it'll be water vapor. The moon is the same distance from the sun as Earth is. It has a temperature of 400 Kelvin on the daytime side. It has a very small atmosphere. What phase is the water on the moon? On the daytime side, well, 400 Kelvin, and what was that tiny number? 3 times 10 to the negative 15. Okay, well, our graph doesn't go down that far, right? So we'll just stop here because it's not going to change our answer, right? If our pressure is super low and 400 Kelvin, yeah, that water is a vapor, right? If I went to the moon and just dropped a glass of water on the surface of the moon, that water would fall to the moon, it would get baked in the sunlight, and it would evaporate away. So, definitely going to be a gas. Okay. Here, getting what about these other planets I just made up? What would the water be like there? 223. So 223 Kelvin, 5 atmospheres. Okay. 220. So 2, 210, 220, 223. Let me write about there. 5 atmospheres. 1, 2, 3, 4, 5. Okay, so that water is going to be right about there. That's solid. That's ice. 430 Kelvin, 7,000 atmospheres. 430 Kelvin, 7,000 atmospheres. 1,000, 2, 3, 4, 5, 6, 7. So 7,000 atmospheres, 430 Kelvin. Yep, that's still liquid. It's hot. That water is way too hot to be 430, yeah. That water is way too hot to be liquid on Earth under 1 atmosphere. But if you pack that water down under 7,000 atmospheres of pressure, it could still be liquid, sure. All right. How about this one? 310 Kelvin, 311, but 310 Kelvin, 44 atmospheres. 310 Kelvin, 44 atmospheres. So here's 10, 20, 30, 40, 44. So we're looking at right here. Yep, that's liquid. Okay, that's liquid. 500 Kelvin, 0.7 atmospheres. 500 Kelvin, 0.7, 0.1, 2, 3, 4, 5, 6, 7. 500 Kelvin, 0.7 atmospheres. When I say 500, oh, it's more like over here. Still, that is hot. That is boiled. That is vapor. 174 Kelvin, 5,000 atmospheres. 174 Kelvin, 5,000? 5,000. 174 Kelvin, 5,000 atmospheres. Definitely frozen. 270 Kelvin, 0.006 atmospheres. 270, okay. So 276 Kelvin, right about there. Oh, 276. Okay, because this line is 273. Okay, so 276, just to the right of that, 0.006. So that'll be, let's see, 0.001, 2, 3, 4, 5, 6. Just there. Yep, just to the right of the triple point there. So just a little too warm. That'll be a vapor. 494.5. All right, 494. I think we could probably just round that up to 500. 0.5. So round that up to 500 Kelvin, 0.5, so there's 0.1, 0.2, 0.3, 0.4, 0.5, right about there, definitely a vapor. 425 Kelvin, 0.7, 425 Kelvin, 0.7, 1, 2, 3, 4, 5, 6, 7, again, definitely a vapor. 138 Kelvin, 0.45 atmospheres. 138 will be about there. 0.7 Kelvin puts it right about there. Definitely frozen. And 550 Kelvin, 1,000 atmospheres. 550 Kelvin. 550 Kelvin, 1,000 atmospheres, right there, 1,000 atmospheres. All right, that's a liquid. So, what are we to make of this? Well, you could have a planet that has liquid water. It doesn't have to be just like Earth. Right? A planet doesn't have to be 1 atmosphere of pressure and 300 Kelvin like Earth is for the water to be a liquid. You can have liquid water at these really hot temperatures if the water is under a high enough pressure. You could have a planet that is a lot like the Earth, the temperature of Earth, but the water will be a vapor. So, this, like here, this is pretty close to the temperature of Earth, but the water's not under very much pressure. So if it's under very little pressure and it's warm enough, it'll evaporate or boil. Right? Just because a planet is the same temperature as Earth doesn't mean the water will necessarily be liquid, and just because it's under 1 atmosphere doesn't mean it'll be liquid. You can have planets that could be habitable. You could have planets that could have lakes and oceans, even though they're not just like Earth. So when we're looking for planets that could be habitable and could have liquid water, we got to look at the whole phase diagram. We got to look for planets that are anywhere in this green zone, and we'll say, that planet could have liquid water. It doesn't have to be just right along this red line like Earth. Right? It doesn't have to be under 1 atmosphere between 273 and 373. All of these planets here have liquid water, even though the water's hot, because the pressure's high enough. So, okay. All right. Nice. Okay. How do we figure out how hot these temperatures? How do we figure out how hot these planets are? Well, that's what we're going to get to next. So, I hope this is making sense. Post your questions to the discussion board if you have them. Otherwise, on to the next planet property, which is temperature. Have a good one, everybody.